methods you can use to determine if material is good enough for an application. So if a lot of times we tie the manufacturing process with the design and the specific choice of material, for example. But when it comes to the details, such as the thickness, exactly how wide you have to make a beam to resist the loads, that's not really, it doesn't influence in general the manufacturing process. If you're making a casting, obviously you do need to know your geometry very precisely before you start a production. But you can make a casting that's a little bit bigger, a little bit smaller. You're not tied to very specific dimension requirements. So a lot of times we will set the dimension requirements based on the loads applied. And that's what we're going to look at today. Once you have a load applied, the question is, for today, is it going to crack by fatigue? So the fatigue is really when you apply the load back and forth. And we will step down, if you will, one step, probably the next lecture, talking about creep, where instead of being a load that you cycle, it's a constant load. The approach is similar. That's why we start somewhere, and then you'll see the similarities as we start looking at other similar issues. Just for the scheduling in general, so today's Friday. On Monday, Professor Eager is going to continue his part of the class. On Tuesday, I'll be continuing the life assessment, probably looking into creep more specifically. So we'll talk more about plastics on Tuesday. Today, it's mostly intended to metals because we talked about metals as being very more resistant, if you will, to having small cracks in them. So that's why we can design them with pre-existing cracks. It's a safer approach than having to assume that the surface is really good, because in practice it's not always going to be the case. So going back here to this example, just to say that this test I did was by applying a constant amplitude force cycle. So we had, this is really going to be 0, and we have a stress, tension stress, and then it was going up and down in a sinusoidal way. That was the load applied for this sample. We discussed that multiple small cracks start on the inside, but we didn't really know about them, and they're not visible. We were looking at a change in the overall compliance of the sample. This was really a duck bone type sample, so we're looking at a bit like this. So say the crack started right here, maybe there was another one here, another one here, but the overall stiffness of the sample was not changing. So there's no way to know exactly when the crack became visible, or of a visible size, but inside the part. So what we end up obtaining is really, for this loading, the number of cycle to failure. So I call that NF. Say about 200,000 cycle for that sample. So it's a little bit of a black box. You don't know out of that 200,000 cycles how many were for making a 0.2 millimeter crack is about the size you need to actually see it with your eye. So we don't know the time it took to get to that point, as opposed to making it what we have on the image, which is more than 1 millimeter crack. But to some extent, it's a little bit when we talked about the stress intensity factor. We don't necessarily need to know. If this number, if we run enough tests to have a range, we know that's the material property. For this loading, it will fail between 100 and 300,000 cycles. And we can design based on that. But we do have to run multiple tests because it will never fail exactly at the same time. If we use a different approach, and we'll go, let's do it this way. I have this image here of the shaft. We talked about the shaft a number of times. And if it's not nice to be out on the ocean and lose the prop. You have to call a friend or call the mechanics to fix the thing. So if we were designing that prop, knowing that at the very end, the best it can support is a crack that's about half the cross section. One way we can do it is say, hey, you know what? I think I have a crack already to begin with. Day one, I start with a crack here that'd be 0.2 millimeter. So it's visible. In reality, you don't have it, but we'll just say we have it. And now we know our bending load, depending on RPM and everything. We have a good estimate for that. So the way we will evaluate that design is say, okay, so what will be my number of cycle to go from here to there? And that is, as you can probably imagine, it's more conservative because it's assuming a problem to begin with. It's also called a damage tolerant approach. That's the kind of general keyword in the aircraft industry to speak to having a defect to begin with. And I'm putting this size here, so that would be AI when we get to the equations later. Initial size of the flaw. And then we have AF, that's the depth of the crack when we reach an overload factor. So in this case, it would be 12 millimeter, right about. Oh, more than that. 32. It was big shaft. So now this sounds, maybe this sounds a little easy or complicated. I don't know what you're feeling about it, but it's all we're going to do is use what we talked about for fracture mechanics, the stress intensity factor. So if this load is the same, and we start here, and we know that K, now we're going to use delta K. It's a variation. Is delta sigma square root of pi a plus change. So I'll put a y here for a random constant that will depend on geometry. We have a round shaft as opposed to a square shaft and all those things. But essentially, this is what we call the solicitation or the excitation of the crack at any point in time. So when we start here, A is smaller than when we finish here. We know, and that's intuition tells us, that the crack is going to grow faster. So we could just go and say, well, okay, I have dA dN, which is my extension of crack length as opposed to number of cycle, equal a fixed number. This number will change depending on how intense the stress intensity is. So that's the overall reason for talking about these complex curves that I showed you 2 or 3 times now. Maybe this time we really make sense out of them. So this is a curve that tells us for a certain value of the demand, right? So all of this here from our previous class on fracture mechanics is the demand for a certain stress. In this case, a stress range. I just put a delta and a delta here. Otherwise, it's the same thing we've talked about. For a certain range in stress and crack length, this is the extent of the demand to grow the crack. And the equation I have on the board here tells us that, and there's a logarithmic function here for that demand of stress intensity. It gives us the shape of how the crack growth rate, that's the dAdn, same thing we talked about here. So I essentially said it's variable. Well, it's going up, all right? It's going up quite a bit because this is a factor of 100 here. It's a logarithmic scale, so you have a factor of 100 in growth rate between the lower level here we call the threshold and sort of an intermediate range here. And at the very end, you will reach close to our fracture toughness that we talked about as well. Now, the fracture toughness in this whole grand scheme is mostly going to give us an idea on how far we can go with AF here before it actually breaks. And we don't have to take it all the way here. Normally, the load's going to be multiplied a little bit, so we'll say, well, by the time we reach here, we don't really mind what's left. It's not a significant proportion of the life. When you think of it in terms of cycle, if when you start cracking till you reach the acceleration regime, you went up by 2 to 500 times your crack growth rate, well, it can't be that the very last bit's going to make a difference. So most of the time, when you start losing here the linearity in this curve, we'll call it a day. That's enough. That's as much resistance you're going to get out of the material as far as life assessment approach. The first portion here, I want to introduce to you the idea that it's not always the same, because in this portion, the microstructure of the material plays a large role on the fatigue crack growth rate. And sometime in design, you don't even know exactly what microstructure you're going to be using. So for an aircraft, for example, a lot of times we will mostly base the analysis in the linear portion, saying something is going to happen to give me a crack that it will already be going to the speed here. It could be a notch. It could be any form of machining defect. Or it could be an impurity in the aluminum. Aluminums, they're so reactive that when they make them in the factory, they always have a lot of inclusions in them. And these are preferential sites to start cracks, micro cracks. So that's exactly the idea. I want to introduce you to this material behavior now, because we'll put that next to each other. This is really the demand. And then we'll call the other one the strength, so we're not confused by it. So the strength, you C or Y, it depends. C, yeah, material constant. C delta K to a certain exponent n. Yeah, but this is not the same n as our strain hardening exponent. This is the n for that slope here on that specific plot. It's very different. So this is our strain right here. For fatigue crack growth. I'm making good progress. So the slides in blue are from a class that used to exist in course 3. I don't think it exists anymore. It was taught by Professor Suresh, who became dean and then head of National Science Foundation. He wrote a book on fatigue, which I brought here. Really good book. If you ever want to chat about all his accomplishments, he was my thesis advisor, so I'll be happy to do that with you. The title page has these little lines that we're going to talk about later. They're not benchmark because now you have to go very high magnification on the microscope, and it tells you where the crack was step by step as you had fatigue in the metal. Now, it's not all metals that will do that, and it's not in all conditions, but gives you an idea that it's really progressive. And the reason we see those lines is the plasticity at the crack tip. You know, when you come and try to inch back and forth and somehow you manage to grow, extend your crack, you will form these little ridges, essentially. So I think it's a great demonstration that everything we talked about so far, as far as really having a plastic zone, because we have a stress intensity and the material will flow, that's a demonstration of that. And you can think that if you have a lot of ductility in your material, it will require more energy to blunt that crack tip and make it move back and forth. And that's why mild steel, for example, will be harder to crack in fatigue. Because you'll blunt it, it'll be like, okay, and it's going to hold very strong. You're going to try to compress it back, nothing's going to happen. So you'll need to raise the load to be able to eventually start moving back and forth. So the hardening and the size of the zone affects whether you can get into this. I mean, it's good looking, but it's really bad as far as, you know, the whole industry. It means that the material weakens each time you go back and forth. So to avoid that, you want to have a bigger plastic zone if you can, and there are multiple ways to do that. Generally, it's with a lower yield strength and a higher hardening. It just goes, you know, against all the other variables. So we talked a little bit about my fluctuating load. I had it here for the test on the plastic. But you can see that I could change this wave function to be with a mean value of 0. So it will go from minus sigma over 2 to plus sigma over 2. And it will still be a fatigue test. It would be a different condition on the material. So one of the reasons for mentioning it is anybody that goes, well, this book doesn't have a whole lot, but the ASM handbooks, they have a lot of fatigue curves. But you have to start thinking, well, am I doing tension, or tension compression? And start looking at the right curve when you compare material. If you want to do a life assessment, you'll have to determine, just by looking, let's say when I did work on the aircraft wing, what's going to happen? Is it going to fluctuate between tension and compression? Is it always going to be compression? If it's always compression, I just want a high yield strength for buckling. I don't have to worry about fatigue. But when I start having a tension component, if it's fluctuating, it could be a different material selection at the end or a different life than if it's tension. Okay, so we take these values into account. What's the amplitude? What's the mean stress? And a bunch of definitions. And you have them in the notes. So I just want to stress out that these are important if you're really going to take a curve out of any handbook or somebody gives you a curve for a new material. What's the loading ratio? What's the loading frequency? It's not there. What exactly are the characteristics of the material as far as heat treatment, for example? The size of the sample. So there are a number of things to take into account before you can say, oh yeah, I can use this curve and get these values here. All we need for a life assessment is C and N. But we need to have it for the right loading ratio, that's R, the right material, and sometimes even frequency or temperature, environmental conditions can play a role. So there's the equation is simple, but the thinking behind it is tricky. You have to make sure that the way these tests were done to give you these curves in the laboratory are close enough to what you're designing. And sometimes you don't know, all right? So we'll be fair. You don't know if it's going to be just tension compression, so you look at both. And in the aircraft industry, it happens a lot. So we'll design a part both using what we're talking about here with the stress intensity, and we will also do it this way for the same part, just as an additional tool to evaluate different options. If you're trying to make a change on something that exists, a lot of times you actually have to be as good on everything if you just want to substitute it without having to go through years and years of certification. And that's why you end up doing this simple type of test, and you do the more complicated test with the cracks that are in there to begin with. Okay, so this was put together for the first time about 50 years ago using the fracture mechanic that we talked in the other class and putting into use for fatigue. And we have the same equation here for the crack growth rate. Pretty much the same tree regime of fatigue for crack growth. This is where it becomes interesting. And obviously I've been doing more of life assessment than most engineers, but I had to go back to these notes sometime just because of the way they were put together. It's so simple. So you have the differential equation, the integral at the bottom on how to go from, we have essentially now we're substituting. So we have the two equations that equal each other. The Parise Law is this one, modified a little bit. But you put the K, all you do here is you put K from our demand right into the Parise equation. So you eliminate K as a variable, and now you can solve for the crack length as a function of load and mostly load, number of cycles. So what you come up to is depending on what it's M now. I think it's actually a good idea. we'll put this as m so it doesn't get confused with the strain hardening exponent. So depending if the value of m is exactly 2 or a different value, the slide number 14 allows you to determine how many cycles it's going to take to go from one crack length to the other. That was our very objective here. It's not linear. It's some form of exponential function. By the time you know your material properties, C and M, you essentially can solve the whole equation. You need to know your stress. Or you work it the completely other way around. If you happen to know what the stress intensity factor is, and I think there's another equation for that. Yeah. So if you know what your stress fracture toughness is, and your final crack length, I'm on slide 18, and you know your stress level, you can determine the stress level. So it works both ways for you, and that's something more to use on a failure analysis type approach. And I mentioned that in the introduction, but that was the hardest part as far as the equations. No more equations, guys. We're good. Yes?
How do you derive Kc?
Kc came in as saying your crack. So it means that this whole term here, you can put it there, essentially.
It's saying you can derive what the final crack length is by using Kc?
Yes.
How do you calculate Kc?
Well, you have to run a test in the lab for the same material. So it is that's what it. All of this become trying to sort in your head that you have a demand and a capacity, and you were right there. If we don't know stress level, so that would be sigma in this equation, but we know what's the fracture toughness, and we know the final crack length, say right here, it's a one-step equation to know what the fatigue is not really even involved at this point. It's a one-step shot to have a good idea of bending stress for this geometry. So it's very powerful. It's never 100% precise, but it's definitely the best we've got. And I do want to say that in general it works for fatigue, but if we had a thin sheet of metal that's very ductile, a piece of steel, we can't use those concepts. Yesterday we talked about the indent and the elastic field that was around it, that was putting it back in compression after the fact. Well, the whole idea of fracture mechanics, and this is the type of sample we make for a fracture mechanics test normally. So it look like this, like a Pac-Man type specimen. So you got the holes. You're going to load it here. You'll form a little pre-crack by fatigue, and then eventually you just open it up to get an overload. Now, if it's a plastic or a very ductile material, and it turns out your plastic zone become this big, just for an example. So that's my plastic zone here after the pre-crack when I try to do my K test. Well, my stress field that I assume, and we're going to call this linear elastic fracture mechanic. That's K. Our stress is supposed to go to infinity, but in reality, well, it stops here, and do it this way, well, it's becoming, if our actual stress is, we assume it to be that way, in reality it's probably going to be like this, and it's not precise anymore because our plastic zone is not small as opposed to the overall sample. So I just thought that was about the right level to warn everybody that there is a limitation here, and that's why we keep referring to linear elastic fracture mechanics, and we always need to have a small zone here. It is true when we have very big samples. Sometimes you have a thin sample of a very ductile material, and now you have to use other methods, and we'll cover that for sheets and other applications. So that what I was going to say, for fatigue, normally K is small. If we're going back to one of the plots we had, so it's a log scale here. If the failure of the material is at, say, 50 megapascal square root meter, when it starts to crack here, it's of the order of 1 to 5. It really depends if it's aluminum or steel. So you can be in a condition where you can use all the equations we talked about, but not all the way to the fracture toughness. You may have to stop before that. But you'll have to stop normally when cracks are already pretty big. So it's not necessarily a big problem in terms of a fatigue life assessment. It could be more of a problem, and that's the reason I was mentioning it, for using the equation here. Because this equation, it takes you all the way to the failure load. And if your part is too small, it's possible you cannot use it. But there are other, I mentioned in the introduction the J integral. So it's a method that will allow you to take into account that you have a lot of plasticity in a small sample, and do the solution very precisely, but it's a lot more effort to do it. It's based on the same general idea, but it's just a lot more work. All right. So we talked about the striations. You may have not have seen the book. So the scale here is only 1 micrometer. So this is magnified approximately 15 to 30x, 30,000x. So it takes a scanning electron microscope to see those little lines. Just an optical microscope would take you up to about 1,000x, and it's all going to be blur. But when you go to a higher resolution, then you use electrons instead of light. That's where you can start seeing these. And you also see the little precipitates. These are the precipitates in the aluminum. And we talked about them as being a source of strengthening. But they are not so much of a great obstacle to grow the crack. Their effect is really on the hardening and the yield strength of the aluminum. All right. So if I'm plasticity, and I know Professor Eager used these the cards to show you plasticity will be shear, right? It's true at the crack tip as well. So when you're at the crack tip, and let's see, get into more detail here. So if we have shear at the crack tip where we want to have plasticity, well, I guess you'll see, you can probably see that it's not possible to just have the shear like I've shown. You need to have a little bit of other mechanism than just shear to be able to keep the geometry in place. But we'll take it as the major deformation. And then there are some accommodation that needs to take place at the same time. Well, if you're able, when you're very small, say there's a grain, okay? There are grains, so that's not a bad assumption. I'm going through a grain, and I want to have this shear. If you remember, a grain is a crystal. It has all these very specific orientation of atoms. It will want to do the shear in a very precise orientation inside that crystal. And that's why at small plastic zone, if the plastic zone is only within a grain, the material will, the crack will be forced to follow certain characteristics, certain planes in the crystal. And that makes this part of the fracture more difficult to predict precisely. Because if it turns out you got a big grain that's oriented in a way that's hard to shear, to start shearing it, then for a little while you have more resistance. So your crack growth rate is going to be less to enter that grain. And then you go through these little tiny grains that are just going to go faster among those. So that's why I did, if you remember when I showed the graph, I said the first regime, we call it threshold regime, you are dependent on what's happening in your microstructure. Sometimes you may have grains that are big and grains that are small. It'd be very different than all grains are big kind of situation. And it's also something we discussed in the intro, that at that point, big grains is good, because it means that, say, my crack wants to go in a grain that's oriented this way. There you go. My crack wants to go this way inside the grain, but really when I'm at the level of the sample, my driving force would like to bring it this way. So now it has to take a detour with a reduced, what we call the effective or local K. So the stress intensity to grow a crack like this, when the stress is this way, is not quite as big as just to grow it straight out, like we talked about. So that's a little bit what this portion of the slides talk about, that you'll have roughness in your fracture surface, in your crack, that is related to the microstructure. The grains, the crystals, sometimes the precipitates may trigger turns in the fracture path. That's an example. So you see it's really going at 90 degrees for this specific crystal, because that's where the shear can actually take place. Shear can't go straight through, so it have to go up and down at plus or minus 45 degrees. So when you go through a series of these loading and unloading, you form these rough surfaces, and there's no specific significance to, this sequence can happen, but there are a lot of different sequences that can happen. And so that's again for a low stress intensity. And what happens sometime is the crack tip here will shear some this way. And the consequence of that is you'll start rubbing between the two fracture surfaces you created. And you could probably think of it this way. It's a good thing, because now when the crack is trying to close, there's something stopping it. So it gets less of an amplitude of deformation in the plastic zone, and you don't have as much growth. So you're reducing the variation of stress level at the crack tip. So it's opening. The extreme limit is I open the crack, I bridge it, and I remove the load, and then now I apply the same load again. Nothing happens. There's no fatigue anymore. So it's the same idea, except that it's maybe going back down half the way. It crushes on the opposite fracture, and then it does go back up again. It happens a lot, and it varies obviously if you're loading with your mean load. So if you're loading like this, it will happen. If you just say, oh, I'm going to load really like tension, then it's possible you don't have any closure of the crack. So that's why dealing with the first part of the curve is tricky, and to be conservative, we go more in what's called the Parise regime. The Parise regime is what gives us this equation here. This is the Parise equation for strain. And the reason why this is now less dependent on even grain size and a lot of other things is now we're deforming enough, we're really more into of a tensile specimen type loading. We have a big plastic zone that involves more than the grain, and it's by blunting and resharpening the crack tip that we can form those striations. There was a question, I believe, last class about striations in plastics, and I mean at the end the plastic will go through the same process as here as far as opening and closing, opening and closing. It's just a question of whether you're going to see little ridges on it. It's nice to see them, but if you don't, you still have where the crack started, where it ended, and you have some idea how much the time it took to get from one point to the other. What we also do, if we want to create this type of curve, the Parise equation curve, and get those coefficients for a polymer, we can keep track of the crack when we're doing our Pechmann test. It's here. When we're doing this, we can really keep track of where the crack is. We don't have to go back after the fact on the microscope and say, oh, it was here at that point in time. So as we do the test, and even from just the compliance of the sample changes with crack length here a lot, we figure out that curve. So from an assessment standpoint, we don't need to go and look at striations. The same way that for fracture toughness, we don't go at the plastic zone size. I'm really trying to introduce you to it in detail so you have an understanding of why is it, for example, that the cyclic load will really grow a crack. And the answer really is by blunting it and resharpening it. Blunting it, resharpening it. Ceramics are a little bit the same way. You'll have some plasticity in ceramics, so you can have fatigue in ceramics as well, structural ceramics. But the Parise equation, this curve here, will be a lot steeper. So for a more limited range of variation in your stress level, you have a much bigger change in a crack growth rate. And you could when they put stabilizers, sometimes it's to help prevent these cracks that are forming at the tip where you have some plasticity to grow too fast. The idea is to add crack arresters, so you can have more plasticity and absorb more energy. But it all boils down, I mean, this plot, as far as dealing with any cyclic load or constant load, which we'll talk on Tuesday on constant load, is very helpful. Obviously, you have to keep in mind there's language involved between what is the excitation we're putting on the material as opposed to what is really the response of the material that we essentially always end up running a test to determine. And everything else that's in between is for us to understand when we get results that are different, roughly what happened. So we raised the yield strength. We thought it was a good thing, but now we have a lower fatigue strain. Well, we know now that the bigger the plastic zone, the more resistant the tip will be to deforming back and forth. That's really the way to think about it. That you'll need more K to move this chunky plastic zone to get it to smear and move any further. Well, I would welcome questions at this point. We have a few minutes. Anything that comes to mind? Yes?
So that basic trait then between yield strength and fracture toughness, that design decision, I assume, largely comes down to how much confidence you have and what the maximum load is that you'll see, what kind of safety factors you're working with, that sort of thing.
Okay. So the question was between using the yield strength or the tensile strength as a design criteria, or using the fatigue properties as a design criteria, a little bit. And the answer is, it really depends on your application. If it's a compression application, the compression part of the wings on an aircraft will be determined by, you'll go for a higher compressive strength, yield strength. The tension part, you'll really be worried about developing cracks, environmental stress cracks, and that will be your design criteria. You'll say yield, you know what? Maybe I'll use it as a quality control, so I'll keep track of it, make sure my material is all good, but it's not what's going to govern the design. That was a good question. Anything else? Yes?
So on that, up there you have the stress, amplitude and all that stuff. What stress is that? If I were to run like an FEA model on something and I have, loading case 1, loading case 2, is this going to be like max principal of one and then min prin of the other?
Well, okay, so what we talked about is mostly unidimensional. And if you go to FEA, yeah, you'll look for max principal, because if it makes sense for that max principal to be a location of initiation. So you have to identify your location of initiation and look for the maximum tension there. And if you have combined loading, you have to include other factors. Right now, we've been concerned with a crack this way, and we're trying to open it up this way, but we'll definitely talk about sometime you can have multiple loading conditions applied. Very good.